It's a great honor to be here. And you know, it's amazing. My career has been really quite long, I guess stretching back over 50 years. And just walking into the auditorium tonight, I met Mike Ballister outside, who was an engineer at Green Bank during my very first observing run back in 1970 at Green Bank, West Virginia, using one of the NRAO telescopes. And then I look up in the audience and see Joe Taylor, who's also a Jansky lecturer, who studied pulsars, went and shared an office with him at UMass. And it's fantastic to see these people again. And I haven't seen Joe probably in 40 years, maybe 30 years. Yeah. So wonderful to see everybody here. Also a huge number of young people. Now I'd like to make this talk reasonably informal. I don't know what Jansky lectures have been like in the past. I've tried to make it very publicly accessible, so very little technicalities, but what I'd like to convey is a little bit of physical intuition about the things you're looking at. And what I really want to introduce you to is this ALMA array, which Tony Beasley mentioned, and it's the big new telescope on the horizon, just getting underway in the last couple of years. And so this animal here, how many people know what this animal is? I thought initially it was a llama. It's not, so see some hands go down. Okay, what's the next choice?
Vicuña. It's called Vicuña.
Oh, you guys are too smart. So that's in fact what it is. It's a smaller version of the alpaca. But it's here because it's a beautiful picture of some animals that are looking on the horizon. What on earth are those human beings doing over there? And in fact, they're constructing this ALMA array, which I'm going to focus on during this talk. So it's in Chile. And a little bit of introduction to the science before I get to the telescope itself. The kinds of things I want to convey in this talk are the things that give me joy in doing astronomy. And one is, of course, this new telescope, which vastly increases the capability. And let me mention where I started out in this field. The first telescope I used at these very high radio frequencies was a 10 or 11 meter telescope in Arizona on Kitt Peak, at Kitt Peak National Observatory, run by the NRAO. And we had receivers which were a factor of 100 less sensitive than the receivers we're now using at ALMA. So with one single telescope, 10 meters in size, the ALMA array is 64 telescopes, most of which are 11 meters in size. So a vast increase in sensitivity. And obviously, as you increase the sensitivity of an instrument, you can look at fainter objects, you can look at more distant objects, smaller objects, and it vastly increases the scientific potential. And this particular field, which has had such great diverse potential, is really just coming of age now, because the instrumentation in the past has been really relatively primitive compared to what exists at centimeter wavelengths. So I'll harp on that a little bit. But I want to also describe a little bit what you gain with multi-wavelength observations spanning the whole spectrum. You see things that you couldn't possibly see in the visible, and what you see in images, even the images taken with the Hubble telescope. And the other thing I want to stress is, to me as a scientist, the joy of doing science is actually the moment of inspiration when you suddenly realize something. And that inspiration doesn't always involve expensive multi-billion-dollar instruments. It involves recognizing something that other people haven't appreciated. And the prime example I tell my elementary astronomy students is something called Olbers' paradox. Heinrich Olbers, 200 years ago, realized, looking up at the night sky, most of the sky that you actually see is dark. How many people are aware of Olbers' paradox? The non-astronomers, maybe. How many non-astronomers here, by the way? Ah, normal people, thank God. That's encouraging. So this Olbers' paradox is really quite amazing and fundamental. You look up at the night sky, you see a dark sky. And this guy Olbers realized that, in fact, when you see the dark sky, it means that each line of sight you're looking along can't intercept the surface of a star, because otherwise it'd be as bright as the surface of a star. So the fact that you then do not see the sky uniformly bright implies that the universe is finite, either in spatial extent, that is, you can't keep going further and further to eventually intercept the surface of a star, or also in temporal extent. It hasn't lasted forever. Now, Einstein, in fact, ignored Olber's paradox, and that was a major mistake on Einstein's part, because he wanted to have a static, non-changing, infinite universe. And in fact, we now know that it is changing, it's evolving, increasing in size, and also it's only been going for 13 billion years. So, it's amazing that a very simple observation like this, and obviously there are arguments against Olber's paradox for subtleties, but basically it's a beautiful realization from a very simple observation, not requiring a tremendous amount of instrumentation other than the human eye, and it's amazing what comes of that. The same goes with respect to Jansky. Back in the 1930s, he was investigating the possible sources of noise which might hinder telecommunications, and in fact discovered a hiss which he saw increase the noise once a day. The initial belief, apparently, or interpretation, was that that noise was probably radiation from the sun, which rose and set each day. But then very quick observation revealed that, in fact, it rose 4 minutes later. The hiss came 4 minutes earlier every day. So it was adjusted to the positions of the stars in the sky rather than the sun, because the stars rise 4 minutes earlier every day. And eventually, as we now know, it became well known that that radio emission is the emission from the center of our galaxy, detected back in 1930 for the first time. And that was the birth of radio astronomy. It's that kind of fundamental, fairly simple discovery, but people following through with it, which makes science so intriguing. So the other aspect which is wonderful is, you discover things which you weren't aware of. I mean, the pulsars were discovered completely unanticipated, more or less unanticipated. And the other thing is, for a scientist, it's wonderful to try to understand stuff. And it's a real pleasure for us as scientists to go out and be able to understand the things we see around us. So a little bit of appreciation of that is what I want to convey. So back in the very beginning, just to put everybody on the same page, the universe started off as a Big Bang 13.7 billion years ago, hot gas. In the first second of that expansion, all the mass in the universe was in an object no bigger than the sun. That is 1 million miles across. And at that point, if took all this matter in the universe and compressed it back down to that size, the density would have been roughly 100,000 times the density of the nucleus of an atom. Incredible density. But that material was hot, it expanded, driven by both the hot gas pressure and also by the radiation. It expanded, continually doubling every doubling of time in size. So it's basically a free expansion, like when you have an explosion. Okay, so time in this schematic diagram is going to the right. Initially, the universe started off very hot. Now, at present day, 14 billion years ago, what do we see? We see a relatively cold universe around us. We don't see a uniform hot gas, of course. We see, terrestrial temperature planets, suns, cold gas between stars. So the universe has cooled down as a result of that expansion. And the same radiation which was emitted down in here has actually cooled down as a result of the expansion of the universe. Now, the expansion of the universe actually has a very subtle and beautiful effect on the radiation. The radiation which we're seeing in the universe is electromagnetic waves moving through the space of the universe. But the universe's space is actually expanding, which means all those electromagnetic waves increase in wavelength or decrease in frequency. So the original radiation from this hot explosion back here, when the explosion became transparent and then the radiation free streamed, at that point, the radiation was characteristic of a 10,000 degree surface. Now, as the universe continued to expand, then it cools. Radiation cools, and now we see this radiation as a 3-degree uniform background across the sky at radio wavelengths. So once again, amazing discovery that you can actually see the same radiation emitted way back after 400,000 years after the Big Bang, when the universe was a hot plasma, meaning ionized gas, and then recombined, became neutral, and at that point then the radiation just free streams through the matter in the universe. So the other concept which I want to introduce you to, because it can come up later, is the concept of redshift. And by redshift, astronomers mean redshift 0 is here in the present. Higher redshift means you're going back in time. So the redshift just corresponds to the amount of expansion of the radiation which was emitted in the past and then gets to us. So if you're at redshift 2, it means the universe has expanded, in fact, a factor of 3 from when it was actually emitted. So all the photons are shifted into the red portion of the spectrum. So that's almost all the sort of physical explanation I'm going to give you. Now, suppose you start off with this hot gas and let it expand. How do you form what we see presently in the universe? We see galaxies, which are condensations of matter. We see stars, obviously, which formed within those galaxies. So the driving force of that condensation is, in fact, what astronomers and physicists call dark matter, which is a completely, almost essentially completely unknown component in the universe, consisting of about 30% of the mass of the universe. And you need that mass in order to overcome the overall expansion of the universe and let material collapse into galaxies and clusters of galaxies. So what I'm going to show you very briefly is a so-called large-scale structure simulation with just dark matter. And by dark matter, they mean matter particles which don't interact with light waves. So it's non-interacting with electromagnetic waves. So this matter, on the other hand, does exert gravity. And so anytime you have a concentration of dark matter, it will have a higher gravitational attraction there, and that'll pull the so-called baryonic matter, the kind of matter that we see in our bodies, into form a concentration there. So in this calculation, a very simple calculation, by containing perhaps 5 billion particles on a supercomputer, you simply follow the gravity of all these attractions. And the frame of view is expanding as the universe expands. So you'll see material move into common centers as the dark matter attracts other dark matter, becoming more concentrated. This will become a super galaxy cluster at present day. And you can see material falling in along these sort of filamentary structures, which are the filaments and walls of the so-called large-scale structure in the universe. So to give this some scale, this is 200 million years at present day. The scale that we know of in our galaxy, how far is it to the center of the galaxy? Roughly 30,000 light years. So this is a huge scale. This is a scale sort of 20 times as far away as the distance to the Virgo cluster of galaxies. Okay, so if you look at present-day galaxies, what do you see? You see a real dichotomy of galaxies. There are the so-called spiral galaxies and M51, the Whirlpool galaxy is one example. And then you see the elliptical galaxies, which are basically spherical clusters of stars with none of this intricate structure in the disk, which shows up as a spiral pattern. And what's the primary reason for that difference? Primary reason is that these galaxies still contain interstellar gas, which then collapses and forms young stars. The young stars are what you see along the spiral arms, these pink regions. And these galaxies no longer have any interstellar matter. And if you think about it, in order to form stars in a galaxy, you need interstellar matter because that's the source of fuel for star formation. Okay, so these spiral galaxies are remarkable. This galaxy has a spherical distribution of stars. And what you see is projected on the sky, but if you could go from different angles, it would still look spherical. this galaxy is actually extremely thin. Here's one of these spiral galaxies, which happens to be on an aspect such that it's sort of edge on to the line of sight. So the thickness of the disk is like 1/100th the radius of the disk. What is the reason for that? Why do these spiral galaxies have thin disks? Well, if you're thinking it must have something to do with the gas, you're quite right. The gas in the interstellar space is very dissipative. It loses its kinetic energy, and so any motions perpendicular to the disk become damped out by collisions of one gas element with another. And then you're left with the so-called conservation of angular momentum, the orbital motion of the particles. That can't be gotten rid of, and so the material orbits in a rotating disk. So those are the two main players on the scene at present day. And the question is, how do you get to those galaxies in terms of evolution? So the various types of evolution are, of course, interstellar gas, which might be very prevalent in galaxies, can be converted into stars. Once the gas is used up, then you form all these elliptical galaxies with no more star formation. There can also be shape changes. Spiral galaxy is a disk. The elliptical galaxy is more spherical. What's the most obvious way you could go from a disk to a sphere? If you collide two of these disk galaxies together, the stars become distributed in a three-dimensional way. You basically smash these two galaxies together. Now, when you smash them together, the stars usually don't collide with other stars because the size of a star compared to the separation between them is so small that the probability of any two stars colliding is essentially zero. On the other hand, the interstellar gas in the galaxies does collide, and that's one of the projects I'll describe to you later. It's really hard to see where you're going here, but actually somebody in the audience can tell me where what I'm supposed to be talking about. Feel free to ask questions also. Yeah, fortunately, not completely full. So, so this is what our Milky Way looks like. We see a plane of stars in the sky, a band crossing the sky. And it's not just the Milky Way is not just a single band as observed by us. You actually see there are two bands of stars here with a dark area in between. That dark area is, in fact, the dust and gas in the plane of our galaxy obscuring the light from more distant stars. And that's the source of rejuvenation in galaxies where young stars will form. So let's see. In the case of a face-on spiral galaxy, if you asked where would the sun be, it would be roughly 2/3 of the way from the center out to the edge of the disk, outside of the two inner spiral arms. You can ask, what are these pink things you see there? The pink things are places where young stars, which are very hot, have produced ultraviolet photons, which then ionize the gas. And then the pink radiation you see there is actually radiation from hydrogen, protons and electrons recombining and forming neutral hydrogen. So it's actually quantum transitions of hydrogen in the gas, in the ionized gas. So if you want to study star formation, how are you supposed to penetrate these dust clouds? Here you have all this obscuration in the disk of the galaxy. How are you ever supposed to see inside these clouds and see how stars are forming? Here you can see some star formation on the edge of the cloud, but you really like to see in this mass here. Most of what you can see in this photograph is all within about 1/5 of the distance to our galactic center. So very limited distance do you see in the visible portion of the spectrum. Okay, here's the electromagnetic spectrum. And the visible light you're used to looking at with your eyes is this very small portion of the spectrum. And the spectrum goes from X-ray, ultraviolet, visible light, infrared, down to radio. And as you go through the spectrum, the waves have an increasing wavelength or decreasing frequency. Frequency goes higher here. And so the energy of these waves increases as you go in this direction in the spectrum. X-rays, an X-ray photon has more energy than a radio photon. Okay, so Carl Jansky, he made his first observations, I believe, at about 20 megahertz wavelength, or I think that corresponds to 15 meters wavelength, maybe. So very long wavelength right from here to the edge of the room. The ALMA array is operating way up here in the edge of the radio window, in these windows here, where the atmosphere, the opacity of the atmosphere is shown by the brown areas. So the atmosphere is opaque here, transparent in the visible portion of the spectrum. When you move into the infrared, it's semi-transparent in areas. And then in the radio, it's kind of transparent until the ionosphere starts to block radio waves at very low frequency. So the ALMA array is operating in these wavelengths. And obviously, in order to reduce the atmospheric transparency, you want to get to sites which don't have much of the absorption in the atmosphere. So if you ask yourself what is causing that absorption, in fact, it's very simple molecules, like in most cases, water molecules in the Earth's atmosphere. So obviously, you go higher and higher in the atmosphere, you get above the water vapor. And so looking into space, there's not much water vapor above you. So the other concept is that one should remember is that higher energy electromagnetic waves originate from higher temperature objects, and lower energy, like for example, infrared or radio, in general from lower temperature objects. So how do you penetrate that obscuration? So you take a clue from, the setting sun. When you look towards the sun at sunset, the sun appears red, and there's red light near the horizon. That's because the red light is photons, which are longer in wavelength, are less absorbed by the particles in the Earth's atmosphere. On the other hand, the rest of the atmosphere appears blue, and that's because when the absorption occurs here, the blue photons are scattered up in the atmosphere, and then you see them down here. So one reason why I put this in is a example which intuitively makes sense. That is, why do the longer waves reflect or not affect the waves, and why do the longer waves get through an obstacle and shorter waves not get through? Suppose you had a log sitting in the ocean. The log would reflect any long wavelength water waves, but short wavelength water waves would not be affected. On the other hand, if you have a cork in the ocean, a very small object, it will ride up and down with the waves and have no effect. Same thing happens with respect to light waves. Here's an example of a dust cloud along the line of sight to a background field of stars in our galaxy. And this is a visible light photograph, and you can see the dust essentially absorbs all photons from background stars. It's not a hole in the sky, it's simply an area where there's foreground obscuration. Now suppose you then go to longer wavelengths in the infrared portion of the spectrum, then you actually start to see through the cloud because the dust is less absorptive to the longer wavelength infrared photons. So when you do the same thing for the galaxy as a whole, here's a visible light photograph up here. You see that once again the dark obscuration of the dust. Then when you go into the so-called near infrared, maybe 4 or 5 times visible light in wavelength, you actually start to see through that dust, although there's still a little bit. But you can actually see the bulge of stars at the center of the galaxy, which you can't see in the visible. Now suppose you actually want to see what's going on inside of the dust. Then what you need to do is to observe emission from either the dust or the gas which is associated with the dust. And that's where the ALMA array comes in. And that's also where these infrared telescopes, which have been launched into space, come in. So one example is the Herschel satellite, which was launched by a European Space Agency in 2009 and lasted for about 4 years. It only lasted for 4 years because it needed cryogen to cool both the telescope and the detectors, and eventually that cryogen boils away, and then the satellite and detectors heat up, and it's no longer operative in any real sense. So On the other hand, it's operating at longer wavelengths. So remember, the dust is absorbing visible light from the stars, but you have to conserve energy, so the dust will heat up because it's absorbed some energy in that light. The dust heats up to a modest temperature and then radiates energy in the infrared portion of the spectrum. It heats up to maybe 50 degrees above absolute zero or 100 degrees. And that characteristically will mean that it radiates in the so-called far infrared portion of the spectrum. So let me show you what an infrared camera would look like. Suppose you take a visible light photograph of this handsome guy with the bag here over his hand, and then you take an infrared photograph of this person. You can see instantly that any area which is hot, like the skin surfaces, emits a relatively large amount of infrared radiation. The other thing, which is kind of irrelevant for our purposes, but this plastic bag, which is opaque in the visible, it's opaque because the plastic reflects any visible light coming into it. So, and it becomes transparent in the infrared. And then here's an example. This is floor tile, visible light photograph. And then somebody has walked on this floor tile, presumably in bare feet, heated up the tiles a little bit. They've walked away, but then you can take a photograph of it, and you see the heat radiation associated with the fact that the tile is a little bit warmer here than the other adjacent areas. Wonderful the way going to a different portion of the spectrum can open up your eyes to an entirely different set of phenomena. So in the case of the Milky Way, suppose you take the near-infrared image, which was here, where you're starting to see through the dust, and then go to longer wavelengths, you start to see the actual emission of the dust in these regions which are forming stars. And let me show you this particular object in Ophiuchus is one of these nearby star-forming regions, and show you an image from the Herschel satellite, which shows this young star Rho Ophiuchus, a big dust cloud surrounding it, which has a very sort of filamentary and structured, beautiful structure, which you can't really see at all in the visible portion of the spectrum. And then in the background, that's the galactic plane here. So you're seeing emission from star-forming regions along the line of sight in the galaxy. Now this is an object, M16, the Eagle Nebula, in the interior of the galaxy, looking towards the interior of the galaxy, although it's not very far away. It's a star-forming region where a cluster of young hot stars is formed. They photoionize the gas surrounding them, and then there's sort of remnant dust crossing over in front of the background ionized gas. So this sort of takes in a large part of the nebula. The next picture is one that you've seen many times, probably from the Hubble telescope, which zooms in on these structures, which you could see down in here in detail. Really beautiful, dense dust filaments in which young stars will form. Now suppose you go to longer wavelengths. Here is an image at 2 microns, about 4 times the visible light wavelength that you saw with Hubble. This is a ground-based image, and you can start to see through the cloud, but you can see there's some areas of dust which are still opaque, and then there are a few areas where there actually are young stars which have formed out of that dust, where the dust became compressed. This, lastly, is an infrared image from Herschel satellite, showing the infrared emission associated with the same set of dust. Here you're actually seeing the emission from that dust associated with heating of the dust by the stars within the ionized hydrogen region. Okay, so here we'll now get into the ALMA array. This is a picture of the Very Large Array, which is also run by the NRAO, and it's located in southern New Mexico, south of Albuquerque. And it's now called the Jansky Very Large Array in honor of Carl Jansky. It's an array of 27 radio telescopes, 25 meters across, and they operate from 200 megahertz frequency up to about 50 gigahertz frequency. So to put that in perspective, remember I said that Carl Jansky's frequency he was looking at was about 20 megahertz. So this is about 10 times that frequency up to you can do the arithmetic better than me. So these are smaller wavelength radio waves, but higher energy radio waves. So this is a very common instrument at radio wavelengths, an array of telescopes on a baseline where they can be positioned with variable separation. And I'll very briefly just explain how that works, because the same principle is applied within the ALMA array. So the ALMA array is located in northern Chile in the Atacama Desert, extremely dry location. And a number of people here in the audience, like Paul Vandenbout and Bob Brown, who used to be on the staff at NRAO, they were responsible for actually discovering this particular site. Well, not discovering it, but emphasizing its capability for the ALMA array. It's an incredible site. It's located at 5,000 meters, which is 16,500 feet. The highest mountain in the continental United States, Mount Whitney, is 14,500 feet, roughly. So this is higher than any mountain in the contiguous United States. And at 5,000 meters, let me tell you, it's not so easy to breathe, let alone construct a high, state-of-the-art technical array of 64 radio telescopes. So it's an incredible technology feat and an incredible feat that people have been able to do this and have a working array at this point. So the basic science which is studied is high radio frequency studies of star and planet birth, colliding galaxies, early universe galaxies, and I'll describe a few of those. It has 54 12-meter telescopes plus 12 7-meter telescopes. And I should have mentioned actually, it's a partnership between North America, which includes, of course, the US and Canada, and then also Europe, all the European observatory countries, and then also Asia, which is Japan, Taiwan, and I think now Korea. But who have I left out? Anybody? No. You have to be careful in these international projects that you don't leave out some major partner.
In Chile.
Oh, in Chile, yes, right. Whoopsie daisy. See, Tony is actually very politically savvy, so, which, if you know Tony personally, you would never accuse him of that. Okay, you'll get back at me on that. Go home and cancel the check. I'll go to a bar quickly right after the talk. So this is a little PR movie made by the organization.
In one of Earth's highest and driest deserts, the most complex astronomical observatory ever is taking shape. Known as ALMA, it is a vast array of radio telescopes so advanced will peer into hidden regions of space with unprecedented sharpness and sensitivity. Even now, with less than a third of its telescopes up and running,
this movie was made about 3
ALMA
or 4 years
is
ago.
the most powerful observatory of its kind, ready to begin probing the invisible universe. Called transporters, move the ALMA antennas into position
So these
on the
transporters are made
Mars-like
in
landscape
Germany.
of the
And you
Chaknantor
notice that
Plateau.
one had a name put on Otto, and the other one's name
ALMA's
is a
radio
woman's name. I
telescopes
forgot
work
what the name
together
is. What?
to make images
Glory.
of space
Glory.
that get better and better as more of them join the array. The telescope has already delivered tantalizing views of space.
So the last image was a picture of a colliding galaxy, and I'll show you some of the science associated with that later on. So the array was completed just this last year. Here is a picture of the current director, Pierre Cox, sitting on the ground in front of the array. It's one of the few pictures I've seen which actually has all of the 64 telescopes of the array in the picture. It also shows Pierre and this fox psyching each other out. It's not clear who is who is mistrusting the other. But it also is, it's not clear it's the best PR image for the ALMA array, because one, here's a fox living up at 16,000 feet. There must be a little bit of water around there. And then you can also see, of course, snow on the ground and clouds in the sky. But, you know, it'd be nice to have a good image in dry, but it's also nice to see a fox, too. Okay, so these big telescopes, for those who aren't astronomers, the way they're actually scheduled, this is a consortium telescope, collaboration between all, you know, large number of countries across the world. The cost of the array it's more than the Hubble telescope, $1.5 billion. So it's an incredible investment of resources. And obviously the time is incredibly valuable. So the way the time is allocated is once a year there'll be a call for proposals, and people like myself and some of the people in the audience here will write a 3 or 4 page proposal describing the science they want to do, and then there'll be a review panel of perhaps 100 astronomers who get together, read all these proposals. But typically in the first review cycle there were 1,000 proposals, actually 1,400 proposals, and the successive cycles about that same number. So I'm going to show you some pictures which were actually taken because I was on the review panel for 3 years, and one of the perks of that was they actually gave you a trip up to the array. The review took place in Santiago, Chile, but then as a result of going down there and sacrificing a week of your time, you got a trip up to the array. So the array is close to a town called San Pedro de Atacama. And here's a group of us going into a church in that town. I'm going to just show you a few folksy pictures just to loosen things up a little bit. So this is looking down one of the streets of the town, a very beautiful town. It's actually become quite a tourist town and has some dirt streets. No cars are basically allowed in the town. And there are llamas in the main courtyard you can get your picture taken with. There are dogs on the street. Picture of one dog. Basically, it's a town that's gone to the dogs and is owned by the dogs. These dogs, nobody owns the dogs. They're just free-roaming dogs, but people feed them. And every street has 3 or 4 dogs just lying on the street. Totally harmless, very loving creatures. And then the mid-level facility, you have to acclimate if you go up to the high site. Mid-level facility is about 9,000 feet. And that's where most of the engineering has been done and the assembly of the telescopes. And it's also where there's a dormitory where both technical people and astronomers who are operating the array can sleep. So this is the mid-level facility. Here is a picture of one of those transporters, which after the antennas were assembled at the mid-level, then they're carried up to the top of the mountain on the transporter and then put down on one of the antenna pads up on the top of the mountain. I don't know whether this is Lori or Otto, but do you recognize the sex of the transporter? Okay, I have to be very careful with improper comments here. I promise. So here we are actually up on the top, everybody kind of gasping for air. We hadn't really acclimated. You do have to do a health test before you go up, and they give you a little spray bottle of oxygen, which I think is basically a placebo, so that you think that you have some rescue. And people spray oxygen in their mouth occasionally. And then they give you a fingertip monitor for the oxygen. So a few pictures of the telescopes. There, as I said, 2 different sizes of the telescopes, 12 meters and 7 meters. And here's a more distant picture. Here's a single telescope. These telescopes are incredible, each one is an incredible engineering feat because they operate all the way down into the far infrared, looking at photons which are 1/100th of a centimeter in wavelength. And the rule of thumb, if you make a telescope which is going to collect photons, is you need the accuracy of the surface, the parabola, to be accurate to roughly 1/20th of the wavelength. So these structures which are, 30 feet across, have to be accurate to 1 part in 10 to the 5th of a centimeter, like basically a human hair. So could you imagine building something which doesn't expand differentially, exposed to the sunlight, exposed to the wind, and it's a major engineering feat. Also, of course, not cheap. So here's me trying to pose with a few people up there. And this is quite amazing because I shouldn't even mention this. I used to smoke cigarettes and I survived up there. But the woman who's shown here, Jacqueline Bergeron, she smokes these little French cigarettes and it's amazing she survived. Fortunately, I persuaded her not to have a cigarette up there. Okay, so how does one of these interferometers work? So basically you have 2 telescopes, radio wave, a single radio wave, say, coming into these 2 telescopes. The way it works is that the arrival time of the waves, the crests of the waves and the valleys, is differentially timed between the 2 telescopes. How much longer does it take this wave to arrive at this telescope versus this one? And knowing the geometry, you can, the waves are moving at the speed of light. That allows you, if you can time the arrival time difference, that allows you to tell very accurately what the angle in the sky is that these waves come from. So the whole advantage of one of these interferometers is basically that you can get a very accurate image of the sky because you can tell where the photons are coming from much better than if you just had a single telescope here. Is you have a larger lever arm on the waves. So here's a little funky diagram I made. Suppose you were at the beach, water wave coming in, and you had these 2 people who, timed the arrival of the wave here versus here, and by that deduce the direction the wave has been coming from. You could do much more accurate determination of the angle or direction by having one person here and one person over here. There's a bigger lever arm on the measurement of the time of the arrival of the wave. So that's simply what's going on in these interferometers. In the case of ALMA, the furthest separation you can take the telescopes out to is something like 25 kilometers or so. And so it gives you very accurate, resolution, which is better than space telescope by a factor of 10, roughly, because you simply separate the telescopes to get more resolution. Okay, so what do we actually look at? We look at the dust emission, which I've already mentioned, but we also, these star-forming clouds contain complex interstellar molecules. The most simple of those molecules is molecular hydrogen, which turns out not to have emission accessible to these radio interferometers. Instead, the prime thing we look at is carbon monoxide, which is just carbon and oxygen atom bound together by, I think it's a double bond. And the radiation we're looking at is a radiation corresponding to different rates of rotation of the molecule about this axis. It's like a dumbbell, this axis between the 2 atoms. So those various rotational energies are quantized, and the primary photons you look at are these photons from the transitions in these quantum states of carbon monoxide. So here's a spectrum from 80 gigahertz to 100 to 110, 115 gigahertz. Gigahertz is 1 billion hertz. So to put that in perspective, remember Carl Jansky's radiation was 20 megahertz. So this is a factor of 1,000 higher frequency. And these are very high, actually a factor of 5,000 higher frequency. So very high frequency radio waves, but they're signatures of the molecular constituents in these star-forming regions. You might ask, why do I want to look at these molecules? You'd like to know the composition of the cloud, but very importantly also, if the gas is moving towards you or away from you, these radiations become blue shifted or red shifted, and so you can measure the motions in the clouds by looking at the Doppler shift. So this is an optical image of a nearby star-forming cloud in Taurus, the dark obscuration of the dust. What I'm going to show you is one of the most beautiful astronomical images I've ever seen. It's an image made with a radio telescope looking at the carbon monoxide line and coding the motions towards or away from us as blue or red shifted. So the areas which are up in here, where they're blue, that corresponds to gas approaching us. And then the areas which are red are gas moving away. So this might be interpreted, say, as some rotating filament along the site. So here's the kind of thing that you can do with ALMA. You can measure the motions of the gas, watch the overall formation of stars, and plot where, what motions cause the formation of stars. So formation of something like the solar system occurs in these dust clouds. The gas collapses, forms a disk, just the way in a galaxy you form a disk, because any vertical motions become dissipated and you're stuck with some angular momentum, which causes the disk to rotate. The star is believed to form first at the center of that dusty disk. And then the dust which is left over in the disk and gas forms the planets. A planet like the Earth is believed to form first by condensation of the dust into larger so-called planetesimals. And then once you grow to something approaching a sort of Earth mass and size, then you start to pull the gas in and form the gas giant planets like Jupiter or Saturn. So this birth is not an easy path because there's a lot of energy released in the course of the star collapsing, first forming. So schematically, it's kind of shown here. One of these dust clouds collapses, forms a star, forms a disk, and then you have a star lit up in the center, young planets forming around it, and then eventually the radiation from the star pushes the gas and dust away, and you end up with a thing that looks like the solar system. So here's an object which was studied by ALMA in this last year. In the Taurus star-forming region, there is a source called LINS 1551, which is down in here. And that actually corresponds to a star which is already formed, which has a disk around it. You can even see that disk here. And the star is actually ejecting material from around the star off into two jets, which go above and below the disk. More importantly, what ALMA studied actually is this object up here called HL Tauri. It's a star called HL Tau, bright optical star, but it's a young star. It's only 2 million years old based on prior optical and near-infrared studies. And it's located right down in here. And the next image is probably the most beautiful result from ALMA so far. It's a very high-resolution image of that disk of gas surrounding the star HL Tauri. So the star is obviously located right at the center of the disk. The radiation you're seeing here is mission radiation from the dust surrounding the star. You're not actually seeing direct radiation from the star, but you're seeing dust which has been heated by absorption of light from the star and then is radiating in the sort of sub-millimeter to infrared portion of the spectrum. So what is remarkable about this? Why are astronomers so impressed by this image? One is it shows a very, very clear disk around the star, just like we would expect in a forming star planetary system. The other thing which completely blew the minds of people when they first saw these images is that you see within that disk these places where there's not much gas and dust. That is, voids in the disk at characteristic radii. So what could be causing that? The idea which has been advanced is that, in fact, if you form planets within this disk, the planets will perturb the orbits of any dust and gas at that similar radius. And so material will either be accreted to the planet or more likely actually cast to lower radius or to larger radius. So they'll open a gap in the disk. And so these gaps are actually signatures of there being a planet in the disk. So let me show you a model which was derived taking a gas disk, putting in 3 planets with mass about equal to Saturn in that disk to try to explain those gaps. And you can see it actually does a fairly good. The orbits of the planets are these yellow lines, and it actually produces a deficiency of gas and dust here at the location of each one of those here by these astronomers. So another project I want to describe is gravitational lensing of light from very early universe galaxies. And this was something that grew out of observations from a telescope at the South Pole called the South Pole Telescope. Amazingly enough, there's actually an astronomical telescope at the South Pole observing high-frequency radio waves, just like the radio waves being seen by this ALMA array. So that telescope actually did a survey of a large area of the sky, discovered a number of bright objects, and then the people on that project, one of whom was this man, Joaquin Vieira, is now at the University of Illinois. He followed up on those objects using ALMA because the single telescope at the South Pole didn't give you very high spatial resolution, but using ALMA as an interferometer, you can make high resolution images. So the idea is that they're actually, what they're looking at, these bright sources are actually gravitationally lensed background galaxies at high redshift where there's a foreground galaxy along the line of sight. And the mass concentration in this galaxy, or cluster of galaxies, causes space to be curved so that the light coming out of this background galaxy curves around and then enters the telescope, gets focused basically on the Earth here. So if you have a background galaxy right behind a foreground mass concentration, that gravitational bending can produce essentially a lens which magnifies and increases the intensity of the radiation from the background galaxy. So here are the images of some of those objects discovered from the South Pole telescope. The red is the ALMA radiation, and then the blue, I think, is an optical image. And you can see the radiation seen by ALMA is actually distributed in a ring around the lensing, foreground lensing galaxy. Now, a more extreme object I want to show you is one which, obviously a nicer image. The first thing I want to show you is a simulation of this lensing. It's a simulation where they put essentially a black but massive galaxy in the foreground and then let it cross in front of background distribution of galaxies. And where the light paths, where the space is curved around the foreground mass concentration, you see the foreground galaxies bent in kind of arc-like images. So you can see that as it crosses in front of the background galaxies like this one, become a full arc here, which is called an Einstein ring. So that's the effect which is made use of in the next study. This was also done just in this last year, and Catherine Villahakis, who will be here on the staff shortly, in Chile, she actually made this image along with all the collaborators in the ALMA development group. And it's a galaxy at redshift 3.0. So that corresponds to looking back roughly 9 billion years in time in the universe, actually 10 billion. So what's happening is you're seeing radiation from a background galaxy being bent into the so-called Einstein ring by the foreground galaxy, and then you see a greatly magnified image of the background galaxy. So one thing which is kind of cool is that subsequent collaborators realized that the fact that you don't actually see the background galaxy in the images indicates, it can possibly be explained that if there's a sufficiently massive black hole in the center of the foreground galaxy, which is doing the images, it bends the light out of the line of sight, and so you don't see the background galaxy along the direct line of sight. But the arcs are shown here. Enough. Okay, so what I want to describe quickly is 3 projects I've been doing with ALMA. One is studying galaxy merger, and in the next cycle of ALMA observing, we'll have data which will be 5 times better than the Hubble telescope, imaging this merger system called ARP-220. Another project will be probing the gas content of galaxies at high redshift, looking back in time. And then the last project is looking at the central black hole in our galaxy. All of these projects, you know, only the middle one do we actually have data for so far, but all of them are ongoing in the next 6 months. So here's an example of one of these merger systems. This is very large angular scale optical image of a system called the antennae, which is two merging galaxies. You know, if you have two galaxies coming together, they raise tides on each other. So material gets pulled out in so-called tidal tails and then gets pulled into the region between the two galaxies. So here's a close-up of this. And the importance of these systems is not only do you grow a galaxy twice as big, you also precipitate huge amounts of star formation in the galaxy where the interstellar gases become compressed by the collision of the galaxies. So here you're actually seeing radiation in the infrared emitted by young stars forming within the dusty region right there. Okay, let me quickly show you a simulation, once again on a computer simulation, of the collision of two galaxies, looking at the star component in the galaxy. The stars get quite widely distributed. You could form a spherical galaxy. This is the gas, and the gas is more dissipative, so you see the gas actually sinks relatively rapidly into the center of the system. And then the people who did this simulation have actually put in some energy release, so the gas gets ejected out as you form a lot of stars. And so the system which we're studying is called ARP-220. It's probably the most famous of these merging systems. It's a so-called ultraluminous infrared galaxy, has about 1,000 times the luminosity of the Milky Way, but all coming out essentially in the infrared. There are two nuclei in the system. The two nuclei of these merging galaxies are, in this case, only about 1,000 light years apart, 300 parsecs. So it's as though, you know, the Milky Way is, you know, as I said, 30,000 light years in radius. So it's like you took the whole Milky Way and squeezed it down a factor of 100 or 1,000. So this is a little technical, but it shows from the observations we obtained earlier with ALMA in an earlier stage, it shows the kinematic motions as judged from the Doppler shift of one of these molecular lines in the nuclei of these two galaxies. So in this nucleus, we see red shifts up on this side of the nucleus and blue shifts down on this side. So you can interpret this as a disk of gas, which is rotating away here and coming towards you down in here. And then similarly for this other nucleus. And you can easily, just looking at the near-infrared image here, you can imagine that this is a cluster of stars, and then there's a disk here, which is viewed inclined to the line of sight, so the stars underneath the disk get cut off on the bottom side. Okay, so that particular object in ALMA, we're scheduled to get data which will be just as good as the data obtained for this star HL Tauri or that lensed galaxy. And it should be really spectacular because so far in the colliding galaxy system, people have yet to actually see the black holes, the two major black holes which probably exist in the center of that merging system. And we hope actually to have enough resolution to see the kinematics associated with the very high mass in the center of the galaxy. Okay, so let me, if I can take 5 more minutes, describe a project which I've been doing, and I think Tony mentioned it in the introduction, the so-called Cosmos project, which was to study large-scale structure in the universe. And it's precipitated by this movie. This is a picture of nearby galaxies as measured by the Sloan survey, only out to redshifts of 0.2 or so. Not very far back in time, but beautifully showing the fine structure in the distribution of galaxies with a little bit of new age music to make you feel at home in the universe. So, you know, you can see concentrations, you can even see filaments. Each one of these galaxies is basically like the Milky Way. And here in this, it's a real visualization of what the galaxy distribution looks like. They look like snowflakes on a winter day, which you guys will have and I won't. So. I'm going back to California. Okay, so this particular project, Cosmos, we had 1/10 of the time on Space Telescope for 2 years to image a large area of the sky 9 times or 10 times as big as the moon on the sky. And the issue is, why do you want to image such a large area with Space Telescope? You want to do it because the so-called large-scale structure, which I showed you in that dark matter movie back in the beginning, the scales of those structures corresponds to of the order of a degree of angle on the sky. So it's a major project, and we even had an artist friend of mine involved in it, and it's been a fantastic collaboration. We've all remained friends after 10 years of this project. So here's what you start out with. You take an image with, for example, the Subaru telescope on the ground, combine it with the Hubble telescope images, and you see a distribution of galaxies on the sky across the entire cosmos field, and this is only what does that say up there? 3 times? So this is what?
6.5.
So this is only 1/36 of the entire area of this survey. And you can see across the whole area of 2 square degrees, there are actually 1 million galaxies. And you see the depth of the data is such that you actually see back to within about 900 million years of the Big Bang. So how do you map large-scale structure? Here I'm seeing galaxies at all different redshifts, all different distances in this line of sight. Well, you need to somehow separate out depth along the line of sight, and for that you measure the redshifts of the galaxies. So that can be done, and it takes a lot of work for 1 million galaxies. That can be done, and we've done it. And so what I'll show you now is a movie which I made looking at the distribution of galaxies as you move out in redshift, moving back in time to greater distance, and where each galaxy here is shown by a little dot, and then the size of the polygon around the galaxy corresponds to the area which is owned by each galaxy. So the denser the lines here, the higher the concentration of galaxies. And already at this redshift, which is very small, 0.3, you can see clustering of the galaxies. If I, once again. If you move out, you see structures changing because you're going to different depths. And this is a 3-dimensional universe. Here's a filament, very clearly. And it turns out the properties of the galaxies actually correlate with whether you're in a dense region of the large-scale structure or a less dense region. Okay, because time is short, let me move on. Here is a visualization of large-scale structure done by a friend of mine, Miguel Calvo, showing the dark matter structures. And I'm showing this just because they're so absolutely beautiful. Here are the flow patterns as material is gravitationally sucked into the dark matter centers. This is showing the voids and walls around the mass concentrations. And then the overall structure of the large-scale structure. Now the lines, as you see here, are just beautiful, but they're not physical. But obvious. Well, it might correspond to the gravitational attraction between adjacent galaxies. Okay, so, and let me move on. So when you go back in time to earlier, higher redshifts, one thing that astronomers are universally agreed upon is there's a greater level of activity in the universe than there is now. The universe is slowing down in terms of the rate of star formation and in terms of the rate at which black holes in the centers of galaxies are accreting material. So that's signified by the brightness or the numbers of quasars that you see as you move out in redshift. They increase to about a peak at about redshift 2, which is about 8 billion years back in time, and then decrease towards even higher redshift. The same with respect to the rate of star formation in galaxies. Star formation at those epochs was about 20 times as rapid as it is now in the present universe. So one of the projects we've been doing with ALMA is to measure the content of gas in these galaxies at high redshift, which you can only do with ALMA because you have enough sensitivity with the instrument. So this is a graph showing the relative amount of molecular gas in these high redshift galaxies, and they're color-coded by how much time they are back in the past. The Milky Way is here, and everything's normalized to the units of molecular gas content in the Milky Way versus star formation rate in the Milky Way. So essentially all of these galaxies at high redshift have higher rates of star formation and higher gas content. So a large part of the increase in activity at earlier redshift is simply due to the increased amount of gas in the galaxies. So that's one project which we've been doing. The other one is one which is coming up in the future, which is very exciting, which is to look at the material falling into the central black hole in our galaxy. Suppose you look towards the center of our galaxy, what do you see? Visually, you see a lot of dust clouds along the line of sight. And there's 30 magnitudes of visible extinction into the galactic center. What does that correspond to? That corresponds to a factor of 1,000 billion attenuation of the optical light from the center of the galaxy. So you can only see the center of our galaxy looking in the infrared and longer wavelengths. So here is an infrared image of the central region of the galaxy. What I'm going to show you now is, some of you are probably aware of it, some maybe not, is an image of the stars in orbit around that central black hole. So there's a very high resolution image made with ground-based telescopes, charting very accurately the motions of the stars. And so there are a bunch of bright stars there whose positions are noted by the symbols here. And the center of our galaxy is a radio source called Sagittarius A star, discovered in the radio by people working at NRAO. And it's a point source of radio emission with relativistic particles producing the radio emission here. So astronomers call it Sagittarius A star. And then in that surrounding area are these stars, which their orbits are shown in this time-lapse movie. And you can see the stars in motion. And this star obviously came in close orbit around that center and then was flung out. So there was some mass there which caused the star to reverse its direction and come back out. And by analyzing the rate of change of the motions of the stars, you can deduce what that mass must be. And as many of you know, there's a black hole, postulated to be a black hole here, with a mass of about 4 million times the mass of the sun. Now, despite the fact that there's this radio emission which has been seen, that's radio emission probably from some jet-like plasma around the black hole. We've never actually seen the actual material falling into the black hole. And one of the projects that I'm doing at ALMA with a bunch of collaborators is looking for the ionized gas which is falling into the central black hole. And we estimate with the great sensitivity of ALMA, and because it's at these long wavelengths, you can see through the dust, we can detect something like a small fraction of a solar mass, roughly a Jupiter mass, falling into the central black hole. So that's, a project which is ongoing. Who knows if we'll see it? We don't know if it actually exists, but it's reasonable to expect that level of plasma or ionized gas around Sagittarius A star falling into it. And so stay tuned. You don't have to pay me again to come back. I'd be so happy I'd come for free. Okay, so let me make a few closing comments. A lot of us like to dream and wonder when we look up at the dark sky. Very few of us, as Olbers actually had this realization that there's significance in the dark sky. But we all take solace from the fact that the sky gets dark at night. Obviously, we can sleep, but we gain a certain solidity to our lives that way. In addition, some of the aspects I've shown here is that our life comes from this darkness. For example, if there wasn't dark matter in the universe, we wouldn't form galaxies. the universe, the material in the universe would just expand away and not condense into galaxies, clusters, and eventually stars and planets. The other thing is, of course, in these dark, dusty areas, that's where you form planetary systems like our own. And so we owe our existence to those dust regions. Of course, you know, the original explosion of the universe, all the atoms which came out of that hot explosion were essentially just hydrogen and helium. And all the heavy atoms you see in your bodies were atoms fused together into heavier nuclei in the centers of stars. And then after the stars evolved and underwent an explosion, the material put back in the interstellar space. And then in the next generation of star formation, accumulated back into a forming planet system, which became the sun 5 billion years ago. So, you know, these dark areas, which to the visible light observer, you know, wouldn't really interest you. In fact, we owe a lot of our existence to. So a big pleasure to me is to understand what you see. A pleasure is also not to understand, because, you know, you don't want to understand everything, otherwise life becomes boring. You want to have challenges. But, you know, you kind of think, when I was first doing astronomy, we're going to solve all these problems, and then, you know, poor people will come after us. There's not going to be anything to do. But inevitably, you find the more you know, the less you, the more you learn, the less you know. You keep finding new things in nature, which are just wonderful. But for being a scientist, the wonderful thing is with integrity, you try to produce a unified understanding for what you're seeing. And that's a tremendous joy. It's almost like the artistic joy of, you know, making a beautiful painting and having everything work together. It's creative at the one time, but it's also very beautiful. So, you know, just to remind you, and I often tell my students or any public lectures that it's incredible where we've come from. You know, in 1930, Carl Jansky made his first radio frequency observations. At that point, we didn't even know about radio astronomy. And David actually tells me that, you know, he'd never even heard the term radio astronomy at that point. So, you know, it's incredible where we've come from. On a more fundamental level, just look back, you know, essentially all we know about the universe is what we've gained in the last 300 or 400 years. And most of it within the last 100 years. Some of this is technology driven for sure, but it's incredible what human beings have done. We've built optical telescopes, radio telescopes, you know, which are basically, you know, you're taking iron out of the ground or aluminum, you're taking sand off the beach, melting it, producing glass mirrors. And through human ingenuity and understanding, you're making something that collects light. It collects these photons, which were emitted, you know, 13 billion years ago back in the universe, long, of course, before human beings were even thought of. Well, maybe somebody thought of them. I don't want to get into religion. Pardon me. What a bad way to end the talk. But, you know, it is really wonderful what we've done. And it's not a matter of arrogance. It's an appreciation of, you know, the level at which human ingenuity can work in really fantastic ways. And so that's the kind of closing thought of like, and, you know, it's going to keep going on for ages as long as we don't do something bad. So I'm going to stop there just for any young people who are here, and I know there's a 5-year-old here who's kind of awake. Astronomy can actually be fun. So this is our team meeting of the so-called Cosmos Survey project. And, you know, they're going to have it at a castle in Germany called Ringberg Castle, which the astronomers here know. And it's kind of a forbidding place down south of Munich. And I said, I'm not going back to that place unless you have the meeting at Oktoberfest. So at Oktoberfest, we took the whole group, went into Oktoberfest. Gunther Hassinger, who was the host, X-ray astronomer, he rented a table at the Oxen House. You can see the poor oxen up on the spit behind. And, you know, astronomy is wonderful. You go to these places, you have beautiful young people that you work with, and it continues. So let me encourage anybody who's interested in it to start doing astronomy. But you know, I'm sure in other areas of science it's also wonderful in the same way. So thank you very much.